In this example, we're going to look at how a power series can be rewritten as a rational function. So let's take a look at the series we'll be using. We're going to be looking at the series n equals 1 to infinity of 1 over the quantity of x minus 9 all raised to the power of 3n minus 1. Now, if you list out the first few terms of that series, you'll see that what it's going to look like is a function that has an infinite number of terms. And we want to write that in a more simple way so that it doesn't have infinite number of terms. And so we're going to try to rewrite it as a rational function. And so what we're going to do is we're going to use our exponent rules to rearrange this series so that we can write it as a geometric series. Because once we have it written as a geometric series, we know that if that series converges, we have a finite sum of 1 over 1 minus the common ratio. And that would help us put this series in terms of a rational function. But that will only work if the geometric series converges. So we'll take a look at that towards the end. So let's do some rearranging with this series. I am going to use the rules of exponents to rewrite the denominator. And I'm going to rewrite the denominator as x minus 9 to the power of 3n times x minus 9 to the power of negative 1. And because I have an x minus 9 raised to the power of negative 1 in the denominator, I can rewrite that with a positive 1 exponent if I put that x minus 9 in the numerator. So that's the first thing that we're going to do. So just using the power rules, I'm going to rewrite the series as n equals 1 to infinity of x minus 9 all over x minus 9 to the 3n. Then, because that x minus 9 in the numerator does not have any n's in that expression, so we are going to pull that x minus 9 out in front of the series. So now we have the series n equals 1 to infinity of 1 over x minus 9 to the third, and then instead of writing it as to the power of 3n, I used the rules of exponents again to rewrite that whole ratio to the power of n. And then, of course, we still have a factor out here in front that we have to make sure to carry down. Now we're almost there. In order for us to rewrite this in the form so that it's a geometric series, it has to either start with n equals 0 and have an exponent of n, or if it starts at n equals 1, then the exponent needs to be n minus 1. So because we have an n equals 1 here, I need to rewrite this so that the exponent is n minus 1. So in order to rewrite that exponent as n minus 1, I need to pull out a factor of 1 over x minus 9 to the third. Then we'll have one less factor, and so then I can rewrite it as n minus 1, the exponent. So when we do that, we have x minus 9. That was the x minus 9 that was in the numerator that we pulled out. And then pulling out a factor of 1 over x minus 9 to the third. That gives us the exponent so that it drops down from n to n minus 1. Now we have this as a geometric series, and then I have these factors in front that will simplify in the next step. And so I can see that the common ratio is going to be 1 over x minus 9 quantity to the third power. So there's our common ratio. So if we want to write this geometric series as a finite sum, we are going to take the factors that are in front here, which when simplified, we have 1 over x minus 9 squared. And we're going to multiply that by our finite sum, which is 1 over 1 minus our common ratio. So for the common ratio, I'm going to put in 1 over x minus 9 to the third. So now we have this big mess that we need to simplify. I'm going to multiply the numerators together and multiply the denominators together. And what we get is 1 over x minus 9 squared minus 1 over x minus 9. And then if we multiply all the terms in that complex fraction with x minus 9, we get the final sum as x minus 9 over x minus 9 to the third minus 1. So now, in order to write it as that finite sum, we need to make sure that we need to find the values of x so that the common ratio is less than 1. Or I should say the absolute value of the common ratio is less than 1. So this is what's going to make it so that it can converge to this finite sum. So I have the absolute value of the common ratio has got to be less than 1. So I am going to rewrite that as a compound fraction. So the common ratio is in the center, and then that needs to be greater than -1, but less than 1. When we simplify that, when we solve for x, it's going to have to fall between 8 and 10 in order for this geometric series to converge. If that value of x falls between 8 and 10, then we can write this series that we had at the beginning, this power series, as a rational function here that's x minus 9 over x minus 9 to the third minus 1. But x has to fall between 8 and 10 for that to work.